Thanks, James, for the warm introduction. And hi, everyone. So today I'm going to co-present with Michael from Meta. So I'm Bowen. I'm a research scientist from NVIDIA Research. So first, let me introduce our recent work, also presented in CVPR 2025, FoundationStereo, zero-shot stereo matching. So given a pair of stereo image, for example, nowadays you can capture with the Meta Aria glass. Later, Michael will also talk a bit on how they made the Aria glass capable of capturing the sufficient overlap between the stereo images. So the goal of the FoundationStereo is to produce a disparity or depth map without any fine-tuning on the target scenarios. So before we dive into more details, what is the value of a depth camera? So depth is a fundamental signal for 3D scene understanding. So whenever we talk about depth, we'll not only talk about depth, but more about 3D spatial understanding. This can be helpful for fusing to obtain 3D scene geometry and help estimating, for example, scene flow. It can also help to aid many other computer vision tasks like handling occlusions, object or body estimation or tracking, and performing segmentations. So there are also multiple ways of obtaining depth or 3D reconstruction. One popular way is the multi-view reconstruction, for example, core map or VGGT. One issue, though, is that usually for this multi-view capturing, they require you to offline capture multiple images with the surrounding views. And the issue is that for some applications, like embodied AI, we're usually dealing with a single perspective with the egocentric view. And we're also processing over a live camera stream, which is processing over online. And there are many dynamics. For example, when I'm manipulating my clothes or manipulating objects, I want how to live estimate these dynamic point clouds. Since the advent of stereo matching, we have come a long way. Traditional methods such as SGM can be applied out of the box because it doesn't need any machine learning. However, they are sensitive to common challenges in computer vision, such as textureless, reflectiveness, complex illuminations, and transparency. Such depth or point cloud causes issues for downstream tasks. Recently, deep learning-based stereo matching methods has made remarkable achievements. However, when applied in zero-shot setup, they are still far from being perfect, such as the bent walls, twisted tables, and shelves. The limited accuracy and generalization prevent practical deployment in novel scenarios. Today, with FoundationStereo, zero-shot and high-quality stereo matching becomes possible. Just applying it out of the box, it produces clean and sharp metric scale depth. In the lifted point cloud, flat table, nicely curved robotic arm, straight walls with perpendicular corners are all faithfully recovered. So to this end, we revisit the problem of stereo matching by approaching the topic in 3 different angles. First, let me introduce how we scaled up the training data with high-fidelity simulation. Specifically, we created a set of high-quality realistic scenarios in 3D, designed by artists. Each scenario model consists of semantically meaningful layouts and floor plans. We also designed a smart camera spawning strategy by taking into account the attributes of the floor plan. We additionally insert diverse 3D object assets into the background to compose the entire scenes. In total, for the FoundationStereo dataset, it features high-fidelity scene layouts and the rendering produced on 48 A40 GPUs for 10 days. It also covers large-scale and rich diversity populated by various 3D object assets and the backgrounds. We also randomize the camera intrinsics and baselines, so later when the network trains on such dataset, it can be applied out of the box on many different stereo setups. Next, I will introduce how we injected the monocular parallels given the recent exciting advancements in monocular depth estimation. We inject the latent features from depth editing v2, which has been trained on large-scale internet data. A side-tuning CNN adapts the frozen features to our stereo setup. Here shows an image pair with different lighting condition, which could have been yield-posed for standard stereo matching. We found the rich monocular parallel significantly enhances the reliability on regions such as the lamp and the guitar hole. Lastly, we advanced the architecture design to make effective use of large-scale training data. Once we extracted the features and built a cluster volume, in addition to CNN-based hourglass, we add another transformer branch. We downscale the cluster volume and reshape into disparity tokens, followed by a series of transformer encoders. This disparity transformer module further enhances long-range context reasoning along the epipolar line. For example, on these repetitive textures for the fences. Flash attention is also leveraged for memory and speed efficiency. So once we apply this disparity transformer, we can clearly see the depth has been obtained much more sharply on the repetitive texture, on the repetitive fences. Now let's take a look at the results. Here shows the qualitative comparison. All methods are run in zero-shot. Comparison methods are challenged by the reflective floor, translucent microwave, and black holes in the trash can. Ours is the only one that reliably predicts these regions. The difference is more significant when visualizing the point cloud. Methods including Croco V2, Stereo, and IGAF fail to identify the ground plane. Zooming in, the microwave inset within the dark cabinet, as well as the reflective griller, introduce challenges. Moreover, the ceiling and the floor are perfectly straight in our point cloud. The turning corner with vertical wall is sharply visible. Here's a restroom scene, including transparent cleanser bottle and large textureless regions. Nevertheless, FoundationStereo produces perpendicular point cloud around the corner and a nice curvature around the white toilet. We also compare to the state-of-the-art monocular metric depth estimation methods, such as Depth Anything V2, Metric Version, and the Depth Pro. We lift all methods' depth into 3D point cloud and align in the same coordinate space for comparison of their scales and the quality. Thanks to the stereo setup, FoundationStereo produces the exact metric scale for the targeted scene, as other monocular depths show some shearing effects around the wall corners. Here's a video showing the relative depth quality on the local surfaces. First, it presents the Depth Anything V2 and the Depth Pro. The shiny tab presents challenges, whereas ours produces straight ones. Zooming in, Depth Anything V2 has issues differentiating between the depth of the hand and the background sink. Depth Pro has slightly better results, but still kind of noisy. Ours produces a clean and a straight hand point cloud. We are proud that FoundationStereo has enhanced various downstream tasks, such as object scanning, large-scale 3D mapping, robotic grasping, and manipulation. To conclude, nowadays, zero-shot stereo matching is finally beginning to work. Depth sensing now relies less on the hardware. In the past, they usually depends on the involvement of LiDAR, structured light, or time of flight. Today, we're now able to advance with the advancements of the software, like the algorithm and the internet data. And what's even better is that 3D data is now becoming easier to capture with the Meta Aria glass. With that, I will hand over to Michael.
Start this here, yeah. So Bowen talked about the generic sort of like FoundationStereo that runs out of the box. My talk will actually then explain how we can take this and apply it to data that we can capture with Aria Gen 2. And this is the example that we've shown previously. This is just running FoundationStereo on data that's part of our pilot data set. Now, there's 3 items I want to talk about. The first one is the hardware, the cameras. And with the new design that we have for the Generation 2 glasses, we actually added 2 more computer vision cameras. In particular, there's a front-facing stereo pair. These cameras have a resolution of 512 square pixels, a global shutter, and they're tightly synced so that we actually take pictures at the same time. Most importantly, there's significant overlap. It's about 80 degrees of overlap between the two cameras that are front-facing, and that's actually forming the stereo pair that we use for FoundationStereo. Now, the second part is stereo rectification. And if you're sort of like in the community, you know that rectification transforms epipolar curves to straight lines that are scanline aligned, which makes your reconstruction typically more efficient. And essentially, it turns stereo matching into a scanline aligned correspondence search. But more important in this case, rectification actually normalizes out any camera-specific and time-varying projection geometry. Time-varying because, the glasses may bend. And this is actually what allows us to use the foundation models that are pre-trained without specific adaptations to the data that we have from Aria glasses. And then we can use the data from the rectification to also map it back to depth, and then finally go back to 3D world space data. Overall, this is the full pipeline that we run. We take the images from the left and right CV cameras, we rectify them, run FoundationStereo, and then we get a disparity image out. This image is then converted back to depth, and then finally we can convert this to a world space depth map or a 3D point cloud. The two yellow boxes that are in here actually take data or represent data that we collect on the device, which is the online calibration, which updates the intrinsic and extrinsic camera parameters, as well as the camera pose that comes out of the VIO system. So here's an example of what this means. On the left side, you see a camera stream from the computer vision camera. On the right side, you see the per pixel disparity rendered as somebody is cleaning up their house. And you can see sort of like the quality of all the depth that we get with that. In fact, talking about quality, this is just taking the raw data from the FoundationStereo, taking also like the poses we get from Aria, and then just integrate this in a signed distance function-based fusion approach. What you can see is like for all the objects that are in there, it's actually giving us a really good and consistent depth. We see some artifacts in sort of like planar surfaces that don't have texture, and these show up in there, but overall, it's really a very good model and result that we get. So finally, how can we actually make this run fast? Because if you run this out of the box on the GPU, and this is a A6000 that we use for testing, it takes about half a second to run per frame to get the depth out. Now, we took a series of steps. One of them is like exporting this, and then changing a couple of the parameters. For example, we're running this on 16-bit floating point instead of 32-bit. We turn off dynamic batching. In this case, we also reduce the size of the images by a factor of 2, making them half resolution. And then finally also put the stereo rectification on the GPU. With that, we end up with a system that runs with 23 frames per second on this A6000 GPU. But GPUs have evolved. And if you take a modern system like the top of the line that you can get now, which is the 5090, we're actually at 80 frames per second on 256 square resolution, and we can run 20 frames per second on the full resolution data from the cameras. So with that, let me wrap up and saying sort of like Aria Gen 2 stereo, it's really a game changer because it virtually adds a depth camera to your glasses without us ever putting any specific hardware on it that is depth. We pre-computed all of that also like for the Aria Gen 2 pilot data set. So if you're interested, you can directly download that data set and look at the quality that's there. Looking forward, there is room for optimizations. For example, fine-tuning models for the specific cameras we have, improving temporal coherence so that there's less flicker, optimizing the inference, and also like distilling it in even smaller models so that you can overall hopefully get this even faster. And with that, I'd like to conclude the talk part and actually want to say we're going to have a live demo now, if everything works. So this is the fingers crossed moment. And we will have a live demo of this system also at the Meta booth in the exhibition. So with that, let's switch over. right, can you hit V, please? Yeah. All right. So this is essentially on the bottom left. You see on the left the stereo, the disparity map. On the right, that's the normals. And then sort of like, can you hit V once, or and select that V button essentially. So essentially, you see it's a depth map. If I get somebody who comes close, maybe to just like show someone, just see here. Here's my hand, rendered in 3D or so. So you can actually see that it's really working well, and it's really running also in real time here. Right, somewhere back there. Yeah, can we get a V once more, please? So this is just the, yeah. All right. Just so that you believe, this is now a rendering of the point cloud. Previously, we showed you the triangulated depth map. So just to show that as well. Yeah, I can rotating it with respect to the camera here would require us to maybe unclick that V button. Yeah, so. Yeah, so now we're actually moving the camera freely. Or actually the camera is fixed and I'm moving the glasses freely. We're getting lost in 3D through here. All right. And then we can try, if we can, to also switch to the color images, if you can get the texture in there. Let's see. Color. Yeah. So now we have actually, it's very dark in this room, but essentially,
this red light would be helpful, you're right.
if we add more light, it's getting it a bit, let's just see. Yeah. It's a trade-off between, that's in there. So I think so, like with that, let's maybe end it here. You can try it yourself at the booth, and then thank you very much.